Good morning, chemists. How are you guys doing today? It's the 14th, October, nearly halfway through the month. Daylight savings time is not too far off. I never remember whenever that is. Um, but I just remember that this year, not this year, November 2nd. Emily, thank you. Thank you. Um, this is the good one. This is the sleep for an extra hour. The spring one is a bad one. And despite saying this like every 6 months or so, I never remember if it's daylight savings time ending or beginning. Um, and for the past few years, I've made that observation and said, I'm not even going to look it up. And I'm fine with that. But I do know, and yeah, I know that's lazy of me. But I'm not going to beat myself up about that because, you know, there's bigger fish to fry, as one might say. Could everyone in the chat give me the number five if you like fishing? hmm If you've never been fishing, do it. So soothing and relaxing, and it helps me. I have ADHD, and it's really nice to have some quietness and some like it helps my brain focus, which it's weird to say my brain, it helps my brain focus because that's also like saying it helps me focus. Um, but at any rate, um, I just brought up fishing because I said there's bigger fish to fry. What we are going to do today is we are going to talk about balancing chemical equations or chemical reactions. And I use those two terms a little bit interchangeably. I'll say balancing chemical equations, balancing chemical reactions. I'll say them both, and I'll sub them for one another. I will do my best to stay on track or stay on brand with chemical reactions. Um, but I hope that you can see how you are equalizing two different things, and so you have to balance those two. So it is an equation that you're balancing. Now, with that, next Tuesday, we're going to do a review. Next Thursday, we've got exam number two. I'll be posting some review materials related to that, hopefully later today. I had intended to post some stuff last Thursday, but one of my kiddos got sick, so I had to leave in the middle of my last class, and so he was all kind of funky. But anyway, I'll get some stuff later today, and then next Tuesday we'll review for it. Kelly, that was the stuff that I'm going to post. And what I'm going to do is just make homework assignments that are much shorter rather than like one assignment that's, 10 questions. I'm going to make like five assignments that are two questions each. So to answer your question, no, I have not, but that's one of the things I'm going to post today. So I apologize for that. But my thought process with um, more assignments, fewer questions, well, then there's kind of less of a burden to carry with each one of them. But those will be posted later today. Okay, so here we go. One of the first things, or one of the things that we've talked about this semester is physical changes. So we've talked about physical states. Um, we've talked about a liquid right here on the far left-hand side. A liquid, well, if you heat it up, what's going to happen is that liquid's going to evaporate. And so what we observe on what's called the macro level is, well, we see, if you leave a glass on a burner oven for long enough, that glass that's filled with water, half full, is going to be empty if you leave it on there long enough. Now, at the microscopic level, and in this case, micro meaning kind of the molecular, I'll say micro slash, or I'll say molecular slash micro level where you can see those molecules. Now, with respect to these molecules, if you look at all of these down here, give me a one if you agree that they're kind of clustered together. And if you heat them up, what's going to happen is these molecules that are clustered together, the space between them is going to grow. So, like what we see here, and then what we see here. Well, the space between the molecules is going to increase. And that is basically what is happening when we're going from a liquid to a gas. That's what's happening at the macro level, and this is what's happening at the molecular level. So, another way to put this is molecules, let me rephrase it. Liquid to gas. Well, molecules are close. Molecules separate and space out. Okay, and then last but not least is this right here, H2O. Now, what I want you to notice about this is that we've got this right here. We've got this parentheses with a symbol, and this symbol indicates L for liquid. Now, there might be an inclination to say, well, water's always a liquid. Yes, but what do we call water that is a solid? I want to ask you that. And add that to the chat. Yeah, it's ice. Okay, and then, so we're familiar with this. Now, what about water as a gas? Yeah, water vapor is what we refer to that. So, just to give you a little bit of a heads up, this particular transition from a liquid to a gas, you could refer to this as vaporization. Now, does anyone know, and could you add to the chat, what do we call, or what do you think we would call this right here? H2O solid S to H2O liquid L. Melting. Perfect. Now, I bring this up, we're going to be talking more about these transitions a little bit later on, but there are like, you have a little bit of context for these transitions. Now, most elements on the periodic table, I mentioned previously that lots of the stuff on the periodic table we're not going to talk about. And not because it's some sort of like, I have to be the great Oz and keep secrets, but instead because, well, lots of things on the periodic table aren't relevant to like human beings and like biology. Now, what we will talk about are the standard states of elements. So another way of putting this is, does anyone remember the acronym? Last time we talked about it, it was mentioned, and somebody asked a question about it. Standard temperature and pressure. Does anyone remember the acronym that we used for that? STP. So STP, standard temperature and pressure. When you see this standard states, this is referencing STP, which another way of putting it is basically normal lab conditions. And whenever you hear normal lab conditions, think, well, about 75 degrees Fahrenheit. I'm gonna put a tilde in front of that to mean kind of roughly 75 degrees Fahrenheit. Um, and and at sea level. So that's important because what that helps scientists do and what helps chemists do is like if you perform an experiment in Denver and I perform an experiment in, let's go with Belton, Texas. There we go. Anyone from Belton, give a 9 in the chat if you're familiar with Belton. I don't want anyone to say, I'm from Belton. Why are you asking about Belton? I'm familiar with. Okay. Um, if I remember correct, yeah, Belton. There we go. So Denver versus Belton. I mean, in terms of like cultural hubs of the world, they're pretty much the same. But also altitude, they're considerably different. You know, Denver's at 1 mile above sea level, whereas Belton's probably it's probably at sea level. I don't know. It's pretty far inland. So anyway, these standard states, it's important to know what something exists as at a standard state. And there are a couple of elements here. the ones that are that have these boxes around them. I want you to know these as what are known as your diatomic gases. Now, a fair question is, well, what does that mean, diatomic? Let's break that word down. Di, atom. So two atoms. Now, what that means is that if somebody ever mentions like nitrogen, like it, or actually, has anyone ever heard of the blimp, the Hindenburg? Add a three to the chat if you've ever heard of the Hindenburg. The Hindenburg was a blimp back, I think, in the 1940s that blew up, and it was filled with H2 or hydrogen gas. So if you ever hear of hydrogen gas, well, at the molecular or the micro level, what you're seeing is this HH. So two hydrogen atoms. All of these elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, are examples of diatomic gases. Now, when I was in high school, I took AP chemistry. I did not pass the AP exam, so it's kind of like, it's not really a flex. Um, and I remember my teacher said a good way to remember your diatomic gases is she had this kind of caricature, this figure, this person's face drawn. And I'm going to do my best rendition of it. You know, the person had glasses, and then they had a head and hair, naturally, and the nose, and then a mouth that was open but filled with a bunch of teeth. This person's name was H. Broncliffe. H. Broncliffe. That's kind of a, I don't mean any disrespect when I say this. It's kind of a goofy name. I've never heard of Broncliffe. But then again, when you think about any name, it's kind of goofy. My last name is Gray. That's a color, I guess. But also my last name, when my ancestors came to the United States, it was von Grabowski. And man, wish they would have kept that. That's a cool sounding name. At any rate, my point is H. Broncliffe. Well, this is a nice little acronym, or it's a mnemonic, a learning tool. H, hydrogen. Br, bromine. I'm going to check them off as I go through. O, oxygen. N, nitrogen. Cl, chlorine. I, iodine. F, fluorine. So this is always helpful for me to just remember, okay, H. Broncliffe, that's the name of, well, it's a nice little mnemonic. Then I can kind of break this down. Another way that people remember this is they just look at it and they say, oh, okay, well, there are a total of 7 elements that that are diatomic gases. There's a 7. And then if you add all those up, you'd say 1, 2, 3, 4, 5, 6. There's only 6. Well, hydrogen's the other one. Can you give me a 7 in the chat if you are going to be able to answer an explicit question of which of the following is a diatomic gas? Sweet. Now, as a kind of continuation of that, and one thing to remember is that what that means is if you ever talk about bromine gas, well, that is Br2, captured here. And it has that kind of like rust type of color to it. Iodine gas is right here. It's kind of got like a purplish color. Now, what that means is that, yeah, 2 elements of this, what they love to do is they come together and they make one molecule. Compared to something like krypton. What does krypton exist as? Well, krypton just exists as Kr. So if you had krypton gas, for instance, has anyone ever been to a birthday party where they have balloon animals and stuff? Well, chances are those balloon animals are filled with this right here, helium, He. And, if you kind of investigate a little bit, you'd find a canister, you'd find a helium tank. That tank, let's just imagine that's a really poorly drawn tank. Okay, here's the base of the tank. Here's the tank, and then here's the nozzle, the head, that then you've got this valve right there. And of course, you've got the valve right here. Okay, so there's my helium tank. There's my helium tank right there. Okay, if this was filled with helium, it's filled with He, a bunch of He atoms. Are any of these He atoms going to see another He atom and say, oh, cool, helium, helium, let's share electrons? Y or no, or Y or N to the chat is no. And let's think about this for a second. Why is that not going to happen? Well, one of the reasons is that does helium have like a full Kelly, perfect. Helium is perfect. Now, helium only has two valence electrons, but it's good there. It doesn't want to share. It doesn't need to share. Same thing goes with neon. Doesn't want to share. It's got its 8 valence electrons. Okay, then if I were to take something like carbon, for instance, is carbon going to exist simply as C2? No. Helium or carbon is not a diatomic gas. So the elements that are going to exist predominantly or primarily as like one in themselves are these diatomic gases. Can you give me a Y or N to the chat if that makes sense? Wonderful. Okay, great. So on the next slide, I've got our first whole question. It is popping up right now. And disregard answer option D because that's not on there. So don't answer D. Of course, the very first person answered D. So this question at its heart is basically, is helium gas a diatomic gas, or is helium a diatomic element? And if you need to, toggle back to the previous slide. And another way to think about this is, what do we know about helium? Helium is a noble gas. So helium as a noble gas, helium says, no thanks. I don't need to bond with anything. I don't need to gain or share or lose electrons. I'm good. I'm happy. I'm fine where I am. So I don't need to do that. And as a result, helium, what I'm looking for with this one, it's going to be this one right here. Hey. Okay, well, I'm going to go ahead and leave that question up for just a second. 10, 9. Wait, what is CLBR and I? No, I'm sorry. The CL. Okay, I got a private message question and said, wait, what is the CLBR and I again? Not diatomic gases? Okay, well, CL2, BR2. I'm going to erase this. All of these that have the red outline around them, these six, and then hydrogen, these are all diatomic gases. Now, what that means is that they most likely are going to form I2 or BR2 or Cl2. But a fair question is, well, what if iodine, for instance, what if we had a compound, an ionic compound of NaI? What if we made that? Well, that would be sodium iodide. And so is this, whenever I say that iodine is a diatomic gas, well, yeah, iodine chances are is going to form I2. But if I say, hey, iodine as a part of a compound, that just means that you're going to have X being kind of your variable or your filler, and I. Okay. Okay, so looks like, yeah, we got good responses on that question. Um, So can you give me in the chat, and you can send this as a private message. Oh, the results are 67% of the class marked A. Great. Um, and so I think we are good on that. Now, what I want to know is, first of all, do you think that you can remember, memorize, put them on your note card, whatever, your diatomic elements? Give me a 1 to 5. A 1 being, yeah, I've got that. That seems pretty straightforward. And a 5 being, where do I write them? Okay, cool. So the thing, think about this actually. I2 versus I minus. This right here is going to be a part of an ionic compound. And this is known as iodide. This diatomic element is iodine. And I know that gets super confusing whenever you look at things on the periodic table and you say, oh, there you go, iodine, done. Wait, huh? What? I and F, fluorine, huh? What? I want you to just know them as, I want you to be able to differentiate between iodine, which I want you to go ahead and think like, okay, whenever I hear iodine, I think I2. Whenever I hear iodide, then I think, okay, that's a part of an ionic compound. Okay, so the meat of the matter for what we're doing today is we are getting into chemical reactions. And I know I've spent 22 minutes leading up to that, but here we are. Now, anytime you look at a chemical reaction, you've got three major components. You've got your reactants, you've got your products, and then you've got this symbol right here, this arrow. Now, this arrow, sometimes um, you will hear a couple of different words to kind of ex explain that arrow. You could hear yields, you could hear produces, generates. And another thing about these is above this arrow, you might see something that looks like this, a little triangle. And that triangle is a symbol that represents change, or like you might also see a symbol like this, lambda. And that means, well, this reaction takes place with the assistance of light. Now, I'm not telling you those because I want you to memorize those symbols or anything. What I want you to do is be able to, whenever you see a chemical reaction, in the event that you see a symbol above that arrow, don't get flustered by it and be like, oh, that must mean something else. The last thing that you might see is this right here. This arrow going both ways, which indicates that, well, your reactants right here can produce this product, but also this reaction can go in the opposite direction. Now, what that means is that, well, yeah, under the right conditions, you could take CO2 and make carbon and oxygen, carbon and O2. Now, this video right here, which I'm not going to click out because whenever I tried earlier, the link was dead or the link was giving me an issue. What this is basically just the solid carbon. So I'll say solid carbon. And then if you get an oxygen tank, an O2 tank, and you spray that, what happens is that, well, that solid carbon kind of begins to break down and disappear. Why does it break down? Because solid carbon in the presence of O2 produces or yields carbon dioxide. So this solid, not sad, solid plus a gas produces a gas. Now, I don't want you to be like, oh, well, is that always the formula that's taking place? No, it's not. You could have two gases that come together to make a solid and a liquid that make a gas, a solid and a solid that make a liquid under the right conditions. So what I want you to know about this is This is just a model chemical reaction. I want you to know the left-hand side is your reactants, the right-hand side is your products, and then this arrow indicates yields, produces, generates. It's your reaction arrow. Now, one thing that's important to know about any sort of chemical reaction is that before the reaction, we've got our two reactants. Here's a solution that's clear. Here's a solution that's kind of a rust color. Well, we can take that rust-colored solution, add it to this beaker, and oh, look, that looks different. These two solutions combine to make something different. Sure, that's worth noting. But the more interesting and the more important takeaway from this slide is this right here. The mass did not change. The mass was conserved. Now, let me ask you this and add a wire into the chat. If these two reactants produced a gas, and this beaker right here, this is known as an Erlenmeyer flask, if this Erlenmeyer flask was open to the air and a gas was produced as a product, would this mass change? Wire N to the chat. Yeah, we would expect the gas to change because if there's a gas that's being produced, it's going to go off into the atmosphere. Now, what I want you to know about that is, let's say a gas was produced and the mass read, let's go with 168.64 grams. Could anyone tell me what is the mass of the gas that was produced? Add it to the chat whenever you get it. Well, if we started at 100, or if our reactants had a combined mass, Maddie, you're absolutely right. It'd be 5 grams. If our reactants had a combined mass of 173.64, we mixed them together and then lo and behold, a gas was produced. Or heck, maybe we didn't even notice that a gas was produced. Maybe it was odorless. But we saw our mass of our products was 168.64. Well, 173.64 minus 168.64 gives us 5 grams, the difference. So if we saw something like this, we wouldn't go, oh my gosh, the sky's falling. Everything's awful. Oh my gosh, we destroyed matter. No. What happened instead was that, well, one of the products was a gas. Can you give me a 9 in the chat if that makes sense? Wonderful. Great. Okay. Next up, we've got just kind of a review of that. And well, this is something that chemists do. They will capture the gas that's produced. For example, in this mercuric oxide, this solid compound right here. If you expose that to heat, if you put that under a flame, well, what's going to happen is you're going to get 92.6 grams of solid mercury. Well, then, oh, the difference or the mass of the gas is 7.39. Now, with that said, if mercuric oxide, let's say that this was let's just say that it was HgO. And this mercury is Hg. Could anyone tell me what is the symbol or what is the symbolic representation of oxygen here? And what I'm getting at is this O? Is this O2? Add an A or a B to the chat with your answer. Is the oxygen that's produced a B or is it A? I got 2 B's and you're absolutely right. Because, well, it's O2 gas. Now, does that matter if this right here, well, there's only one oxygen. Is that a problem? No, it's not. One of the reasons that that's not a problem is, let's think about this. This is 100 grams of mercuric oxide. So 100 grams, that's more than a few moles. So that's more than a couple billion of this HgO. So we got trillions of this HgO And whenever this breaks down, we'll get Hg, and then we'll have O and O and O. And you know what? Those two will pair up, and they'll pair up in that ratio. Could you give me a one in the chat if you follow that? Awesome. So if you follow that, that's a really important thing to understand about chemical reactions and reactants and products. And if you follow that and kind of keep that at hand, that's going to really help whenever we're balancing chemical reactions. So just another couple of examples of or another conservation of mass. Yeah, gases are products and gases do have mass. Now, with that in mind, here's an example of an unbalanced chemical reaction. Could anyone add to the chat, what is our reactant in this chemical reaction? Okay. So Kelly, you're right. I was really just looking for H2O. H2O is our reactant, and our products are H2 and O2. Can we do that? Can we have one thing break down into two? We can. This is what's known as a decomposition reaction. And decomposition reaction, I'll sometimes refer to those as breakdown reactions because you have one thing that breaks down into two other things or multiple other things. Now, could we have one thing, I'll just label it as X, break down into A plus B plus C plus D? Is that possible? In the words of former Boston Celtics player Kevin Garnett, anything is possible. Yeah, that's absolutely possible. And I don't know if anyone's yeah, there we go. So that's absolutely possible. This is a decomposition reaction where we have one thing breaking down into multiple things. Now, when we look at this unbalanced chemical reaction right here, what's what is the what is unbalanced is my question, really. That's where we're starting. Oxygens. Perfect. So how do we balance them? Okay, well, and actually, if I said water breaks down to hydrogen and oxygen, could you take this statement and produce that chemical reaction? I'd like you to be able to. And you might be thinking, well, why? Or how could I do that? Well, what do we know about hydrogen and oxygen? Well, hydrogen has the symbol of H and oxygen has the symbol of O. What do we know about these two things? They are diatomic gases, or they are diatomics. So when you hear hydrogen, I want you to think, okay, chances are he's talking about H2 unless it's a part of an ionic compound. So it breaks down to hydrogen. It's not going to break down to just H. It's going to break down to H2. And then oxygen. Well, that's not going to break down to O alone. Instead, it's going to break down to O2. Does that make sense? Give me a Y or N to the chat. Okay, great. So if you're thinking, oh, should I be able to, should I be able to do this sort of thing? Yeah, I would say that, taking this and translating it or, yeah, translating it into this is a skill that I want you guys to have, where you're converting like English language into a symbolic chemical language. That would be like a first level question. The next level question would be, okay, now balance it. In which case, you would come up with this H2O yields H2 plus O2. You'd say, okay, well, there's two oxygens. I need to balance those. So I'm going to throw a 2 in front of this. Are my oxygens now balanced? They are, because I got O2 and then 2O. Done. But that presents a little bit of a problem because how many hydrogens do I now have? Well, this 2 applies to everything in here. So it applies to the oxygens just as it applies to the hydrogens. So that puts us at 4 hydrogens. So how would I balance this? I'd throw a 2 in front of that. So 2H2O yields 2H2 plus O2. And it is now balanced. Could you give me any emoji into the chat? Any like smiley face emoji? Okay, cool. Wonderful. Great job. Okay, so we'll go through and just so you know, balancing chemical reactions and chemical equations is something that's it can get kind of tricky and it can get kind of hairy. Is that like should you expect to see the hairiest and trickiest chemical equations to balance? No, don't. Will there be some that are a little bit challenging? Yeah, there will. But there's not going to be some that are just like, oh my gosh, where do I begin? There's 7 reactants producing 12 products. I'm not going to do that. Now, with that said, how would we balance this? This is a nice representation where you've got carbon reacts with O2 gas to produce carbon monoxide. Now, carbon monoxide, if you have any gas appliances, get a carbon monoxide detector because this stuff right here is deadly. And one of the reasons that it's deadly, does anyone know the name of the protein that takes oxygen throughout your body? Whenever you do this, in your lungs, or in your alveoli and your bloodstream, there's red blood cells that they pick up oxygen, and there's a particular protein in there. Does anyone know that protein? I'll give you a hint. It starts with an H and ends with a globin. Ah, great job, Kelly. Hemoglobin. Yeah. Hemoglobin, HB as it's sometimes known. Well, it can bind oxygen, which is great. That's what you want. Unfortunately, it actually wants carbon monoxide more. And so it will bind carbon monoxide. And basically, what happens, or one of the things that happens, is that if hemoglobin binds carbon monoxide, it's not going to bind O2. Your fingers, your heart, everything in your body needs O2. And if hemoglobin's binding carbon monoxide, then you're going to have trouble. And that's why it's fatal. So, CO detector. If you have any gas appliances in your home, please get a carbon monoxide detector. They're like 20 bucks and they can save your life. Um, with that in mind, here's our reaction. Solid carbon reacts with O2 to produce carbon monoxide. Okay, down here, what we've got is our visual representation of that. And this is actually the visual balancing. So I think these are black beans right here, good sources of fiber and protein. Black beans represent our carbon. We've got 1, 2 carbon atoms reacting with 1, 2 O2s as one molecule. Now, just so you guys, when you're looking at this, I do want you to recognize that there is space between these to indicate there are 2 separate atoms there. So we've got carbon, 2 carbon atoms reacting with 1 O2 molecule, and our production is, well, we've got carbon monoxide, one of them, and then another carbon monoxide. This is our balanced chemical reaction. So the way that we would look at that and write that out as a balanced chemical reaction would look a little bit like this. 2C plus O2 yields 2CO. All right. And if you haven't seen this or thought about this already, anytime you have a coefficient out here, this is a coefficient. Could anyone add to the chat? What is this? I'm going to put a question mark. Add to the chat what this is referred to as. I'll give you a little bit of a hint. It's a sub, which is why it's a little bit lower line. Maddie, you're absolutely right. Terry as well. It's a subscript. Subscripts change. So I'm putting this equal sign, subscripts, and I'm canceling out that equal sign because do not change subscripts. Coefficients, however, change as needed. Adjust those as needed. Because that's one of the reasons why if I see this balance or this unbalanced chemical reaction, I'm not just going to go and say, oh, well, C plus O2, done. Because, oh, I was just harping on carbon monoxide detectors. This is a different product. Can you give me a Y or an N to the chat if you recognize that CO as a product versus CO2 are different things? And that's why we can't just go around willy-nilly switching out or changing a subscript, because then we're changing that molecule or we're changing that compound. Okay, so we got another poll question here. And that's up right now. And again, dang it, Joel. Everyone answered D. Somebody answered B. I told you to answer D. Why did I say answer D? Because what this shows is that we've got MgOH. I always like to draw out a molecule. Mg has a plus plus. OH is a polyatomic ion, and it's negatively charged. OH negative. Okay, so there's our MgOH2. If I've got 3 in front of that, well then, how many oxygen atoms do I have? Well, this 2 applies to everything in here. So that means for each one of these, for each MgOH2, I've got 1, 2 oxygens. If I throw a 3 in front of that, that means I've got 6 oxygens. Which is why E is the correct answer. And there we go. Now, I'm going to do another poll here. What is the formula for iron 3 chloride? Iron 3. Let's think about this for a second. If I asked you about iron 3 with these Roman numerals, well, I'm talking about an ion. Do you think that it's, I'm going to write it. Do you think that it's Fe2 plus, Fe1 plus, Fe2 minus, Fe1 minus? Well, all of these answers, yeah, they all include iron, but none of them have the number 3. Do you think that this number is significant? Absolutely. The important thing to know about this is that that 3 indicates something about its charge or the magnitude of its charge. So this is Fe3 plus. Anytime you see that Roman numeral, we've talked about this before, that's a positive charge. What about chloride? Well, so this is Fe3 plus. This is Cl minus. I've got several messages. I meant to put something else. Don't worry about it. Well, let's think about this for a second. I'm going to write Fe plus, plus, plus. Give me a Y or an N to the chat if you think that this is the same as this right here. Yeah, that's a fine representation. Okay, well, chloride, Cl minus. If I wanted this to be a neutral compound, iron chloride to be neutral, then I'd have 1, 2, 3. Does that all sound good? Y or N? Yeah, perfect. So really what we're looking at is FeCl3. So our correct answer there is going to be B. So looking at answer options A and C. Well, answer option C, we'll look at that first. There's a 3 there. but that doesn't say anything about the charge of this iron ion. Now, I want you to be able to see anytime you see chloride or iodide or bromide or fluoride, I want you to think, oh, that's a -1 because I know where that is on the periodic table right here. All of these are -1 ions. Then what I want you to be able to do is also see this and say, okay, well, sorry. So that's out. So answer option C is out because, well, it doesn't really balance any sort of charges. Answer option A, why is that out? Well, this is like answer option A and B are intended to be the most attractive answer options. These are the ones that are supposed to like, one's supposed to trick you into answering the other. Um, but what you have to do and what I prefer to do is I'll look at this and if I saw like manganese or manganese 5. Well, what I'm going to do, just so you guys know, manganese is Mn. I'm just going to write out these positive charges. Plus, 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 plus. There's my 5 positive charges. If I'm making manganese 5 chloride, I know that chloride is -1, so I'm going to say Cl minus. That's 1. So if I had manganese 5 chloride, MnCl, ooh, MnCl. If this was manganese 5, this would still have a charge of +4. Give me a Y or an N to the chat if you follow that. Okay. I want to come up with a formula where this is overall neutral, Cl minus. Done. Done. I like to draw them out like this. It helps me just kind of almost do some accounting. So then my formula would be MnCl5 because I had 5 chlorines. All right. Now this is, yeah, we've done this, so this might feel like, oh, well, this is pretty redundant. And we had 74% of the class answer correctly with B. This might feel a little bit redundant, but it's an important part about balancing a chemical reaction. Now, I've got this link that I'm about to share in the chat. And here we go, FET, Colorado, EDU. And I'm going to share my screen for just a moment so that we can actually do some of this together. There we go. We've got a couple of different a couple of different options. There's the introduction where it's just kind of a visual representation. You've got to have this balanced with this. And then there's the equations where it's just symbols like A and B. But then there's this game option, which is really kind of our best one. Let's go ahead and start with level 1. This says N2 plus O2 yields N2O. Now, if we put this, we've got one N2 molecule. Let's go ahead and check it. Oh, lo and behold, it's not balanced. Why is it not balanced? Because I don't have any products. Okay, so I'll put one reactant, one product. Okay, so now I've got 2 nitrogens on each side. Let's check if that's balanced. Lo and behold, it's not. And at this point, I gotta start over on that one. Oh, dang, it gave me a different one. Let's see. There we go. We're back with this. So there. Okay. Now, the 2 blue balls represent the nitrogens, making nitrogen, or N2. N2O, 2 blue balls, 1 red, or orange. We're going to throw this down. Our oranges aren't balanced. Now our oranges are balanced, but our blues aren't balanced. Now our blues are balanced and our oranges are balanced. Can you give me a 7 in the chat if you follow that? Yes, they are visually balanced, and you can see that. Boom. What's up? What's up? Okay, so that brought up, let me show you this also. I'm going to go back, get that same. I'm going to try to get that. Dang it. Oh, it must be like you conquered that. Okay, so I want to show you this also. We've got NH3. We've got a reactant, a singular reactant, producing N2 and H2. We talked about this where we had one reactant going to two reactants. What type of reaction is that? Add it to the chat. While you're doing that, I'm going to go ahead and try to balance this. Okay, we got two nitrogens, so I'm going to bump this up to two NH3s. And the term I'm looking for starts with a D. Okay, so now my nitrogens are balanced. Hydrogens, not balanced, not balanced, balanced. Okay, so the word I was looking for was decomposition. Add a wire and, oh, private message, I got it right then. Okay, so add a wire and into the chat if this is balanced. You got two nitrogens on each side, six hydrogens on each side. Okay, now everybody, I want you to buckle up for a second. What if I did this? Nope. What if I did this? Okay, now this, we've got 4 NH3, 2 N2, 6 H2. So on the left-hand side, I've got four nitrogens, and then on the right-hand side, I've got four nitrogens. On the left-hand side, I've got 12 hydrogens, and on the right-hand side, or my product side, I've got 12 hydrogens. Could you give me a plus if this is balanced and a minus if this is not balanced? Yeah, I would agree this is balanced. Um, but here's a little detail. We can do better than this. Why can we do better? Well, the reason we can do better is because we can reduce this down. So whenever I click check, it's probably going to tell me to try again. Okay, try again because it's balanced, but it's not simplified. So what that means is that we could take all of these right here, these coefficients, the 4, 2, and the 6, and reduce them down. Does everyone see how they have a lowest common denominator? If we divided all of these by 2, we would get 2NH3. 2 divided by 2 is 1. 6 divided by 2 is 3. So now we're balanced and we're simplified. Could you give me a Y or an N to the chat if you see that? Okay. Now I'm going to swap over here. We got another poll question. And this one, I'm going to edit. So what we have is when the equation for the combustion, ooh, I like this because this is a new piece, or new question, or new piece of terminology. A combustion reaction, or a combustion. When you think of combustion, could anyone add like a word that comes to mind when you hear combustion? Oh, yeah, explode. That's what I think of too. Um, if you drive a car that is not a Tesla or any other electric car, you drive an internal combustion engine car. And that's because your engine has little explosions that take place, or combustion reactions. A combustion reaction, this is one of my favorite ones to learn, was a compound that consists of carbon and hydrogen, also known as a hydrocarbon. Hydrocarbon and oxygen gas. And a combustion reaction will always produce the same two things. I haven't posted the poll yet. CO2, carbon dioxide, and water. Okay, so when you hear combustion, I want you to think hydrocarbon plus oxygen, and Jordan added air plus fuel. Yeah, most fuels are going to be hydrocarbons. Plus O2 yields CO2 and H2O. Okay, now when the equation, I'm going to go ahead and launch this poll right now. When the equation for the combustion of methane, CH4 is methane, is balanced, what is the coefficient? Okay, so we've got, are we balanced right now? One carbon, 4 hydrogens, 2 hydrogens. Okay, so I'm going to throw it 2 in front of this. That gets me to 2, that gives me 4 oxygens. Then that gets me 2 oxygens. I got an O2. Okay, so carbons, hydrogens, check, check. Oxygens. Here's 2, here's 2, here's 2 more. Put a 2 in front of that. Let's see. After I put those coefficients, I'm going to go back and inventory them. Carbon and carbon, balanced. 4, 4, balanced. 4, 2, and 2 more. Does everyone see how I've got this balanced with a 2 coefficient out front? Great. Now, one thing that I'd like to add is this answer option C. C is the incorrect answer. Why is it an incorrect answer? What's different about C versus D, E, A, and B? 1.5. This is a fraction. Yeah. This is not a whole number. And that's one of the important things to remember about or to know whenever you're balancing a chemical reaction. The coefficients have to be whole numbers. So when we looked at this balancing, oh, am I sharing? Oh, good, I am. We always have to have the lowest common number, but it has to be a whole number. I'm going to go ahead and end the poll. We got good responses there. The predominant or the popular answer was D. So good job there. Now, let's do some practice with these and let's see what else do we have. Yeah. So let's balance these out. NaN3 yields Na plus N2. We'll write this on the next line. Close that. And what I'm going to do is I'm going to give myself a little bit of space there. I got 1 sodium on each side. Perfect. I got 3 nitrogens on the left, 2 nitrogens on the right. And yeah. So if I wanted to, could anyone tell me what is the proper coefficient to put in front of the NaN3? And if I get the right answer, or if you guys put the right answer in the chat, there's going to be a bonus point on your next exam. I've got my card here. Okay, we got a 2. Let's see. Okay. And then for the Na, there's another bonus point there. Tell me what that should be. I'm seeing 2. Okay, and then last but not least, what about in front of the N2? And there's a third bonus point in there for you. 3. Okay, let's go back and let's count this up. 2 sodiums. 2 sodiums. 6 nitrogens. 6 nitrogens. Good job, everyone. You got 3 bonus points on your next exam. Okay, you know what we're going to do is, yeah, we're going to go on to the next page. Not that I'm scared of this one or anything like that, but I want to get through these. Okay, so this right here, this is a compound called sodium nitrate. KOH is potassium hydroxide. OH has a charge of -1. Could you tell me when you have multiple atoms that have an overall charge, what is that called? When you have 2 atoms that come together to make something with a charge, a negative or a positive charge. What is that called? It's a class of compounds. Maybe not a class, but a grouping. Yeah, they're ions, but let's think there's another bonus point in there for this. If you got 2 of them, if I said that K plus, that's an ion. How many atoms are there here? 1 atom. Would you agree that this is monatomic? A monatomic ion? Wire into the chat if you would agree with that statement. Okay. So then we've got that this is an ion. What word should come before ion then? Polyatomic. Great. So this is a polyatomic ion. Answer Y or N to the chat. Do you have to remember the polyatomic ions? Did I ask you to memorize the polyatomic ions? Nope, I didn't. I asked you to know that, be able to look at the chart and look at the names and stuff, but I don't need you to memorize those. Okay, so now what we've got is two ionic compounds. Sodium nitrate, NO3, is a polyatomic ion. Potassium hydroxide is also a polyatomic ion. We're going to balance this one and then we're going to call it a day because we've covered a lot of stuff. Lots of review and a good bit of new stuff. So NaNO3, NaOH, KOH, KNO3. Okay, those are our reactants and those are our products. What do you notice, or what I want you to notice, let me rephrase that. What I want you to notice here, that's a great question. It is already balanced, and you're absolutely right. But one of the things that I want you to notice about this is this NO3, it's still NO3 as a product. So whenever you see a reaction like this and you hear about, or we'll balance one more after this. When you see a reaction with polyatomic ions, I want you to think, oh, okay, I see NO3. That's going to stick together. Does that make sense? Give me a Y or N to the chat. So it's NO3 on the reactant side, and lo and behold, it's NO3 on the product side. KOH, that's OH, and that's OH as a product. So when you see a chemical reaction or an unbalanced chemical equation with polyatomic ions, I want you to think, this is good because there's less work for me to do. Because all I have to do, like this NO3 isn't breaking down into anything. So for this one is already balanced. Now, if we go down here, okay, let's look at this one at the bottom. Okay, iron 3 nitrate. We're going to rewrite this. We're going to kind of translate this. Could anyone tell me in the chat, what is the charge of iron 3? +3. Okay. Now, nitrate. Ooh, that's a little bit trickier. But we can use this right here to determine the charge. If I tell you the truth and the fact that sodium has a +1 charge, and this compound, NaNO3, is neutral, can you tell me what the charge of nitrate is? NO3. So this whole thing is neutral, has no charge, has a 0 charge. So think about this almost like an equation. We have Na plus what gives us 0? Would you agree that Na plus, or sorry, positive plus negative gives me 0? Would you agree with that statement? Okay. So I want you guys to be able to see something like this and deduce that, okay, if Na is +1 and this whole thing has a charge of 0, then NO3 must be -1. Does that make sense? Now, let's use the same logic approach to KOH. K has a charge of +1. That's the common ion that potassium forms. Therefore, what is the charge of OH? -1. Okay. Now, if iron nitrate, I'm going to say Fe. If iron has a charge of +3 and nitrate, we already deduced, has a charge of -1, could anyone give me the formula? Actually, let me rephrase that. I know that I've got Fe and NO3. how many irons am I going to have for this compound right here? 1, 2, 3. Iron has a charge of +3, so we could write that as plus, plus, plus. Nitrate has a charge of -1. So I'll need 1 minus 1 to cancel out that positive. So 1 nitrate to cancel out that. Give me a 7 in the chat if you follow that. Okay. Then I'll need another NO3 minus another one to cancel out that positive charge. Give me a 9 in the chat if you follow that. And then NO3 minus another one, a third NO3 to cancel out that last positive charge. Give me a 15 in the chat if you follow all that. Okay, so would you agree with the statement, Y or N, would you agree with the statement that you have 1 iron to 3 NO3s? So it's almost like your formula, Fe NO3 3. Is that pretty close? Y or N to the chat? Yeah. The only thing I need to add is I need to put a parenthesis around this NO3 because I have 3 of them. And I want this 3 to be outside of it because if I don't put it outside the parentheses, then it's going to look like NO33. And we don't want that. So does it make sense to you that this formula right here, this name, is this formula right here? Y or N to the chat. Okay. So we've got FeNO3. I'm going to erase this. And then I'm going to say plus NaCl. Yields. There's a bonus point in it if you can tell me the name of iron or the formula for iron 3 chloride. Think about the charge of the chloride ion and the charge of iron 3. Perfect. Great job, Kelly. And for anyone else who's like, oh yeah, that's what I was getting. Perfect. Awesome. So FeCl3. Could you give me a Y or an N to the chat if you understand how to deduce and put that together? Okay. So then what we're going to do is plus NaNO3. All right. Now I'm going to switch colors for my pen. And I'm going to look at this and say, wait a minute. Do I need anything else to indicate, like, do I need to change this? Does the NO3 need to be in a parentheses? No, it doesn't. Because the charge of sodium is +1. The charge of NO3 is -1. Okay, so these are, I understand, I just might need to write the cheat. Perfect. Go for it. I got a private message that said I might have to use some of this on my note card. Do it. Do it. You know, I would grab some of these. I would just grab this and write it down and be like, write down your thought process for it because that will help you during the exam. Because the exam is not just like, hey, recall this information. Instead, I want you to be like, I know how to think about this. Okay, so I didn't need to put any parentheses around the NO3 or the Na because it's a +1 and a -1. And you erase those real quick. And now what I'm going to do is I'm going to see that these are balanced. I forgot to put my 3, but now it's there. What I'm going to balance first is actually my nitrates. And I mean, could I have started with something else? Yeah, absolutely. But I'm going to balance my nitrates because that's kind of a crooked number. I've got 3 of those, so I'm going to put a 3 out here. Are my nitrates now balanced? Yeah, because this applies to this. It applies to this. It also applies to this. Or I could just rewrite this and say it applies to this whole thing right here. I've got 3 nitrates, 3 NO3s on each side. Now, what did that do? That changed my sodiums. Now I've got 3 sodiums. So I'm going to put a 3 in front of this. Um, let's see. Am I balanced? Wire N to the chat. I've got 1 iron, 1 iron, 3 nitrates, 3 nitrates, 3 sodiums, 3 sodiums, 3Cl, 3Cl. Yeah, I'm balanced. I'm good. Okay, everyone. That's where I'm going to go ahead and stop class. We're done a little bit earlier today. If you got questions, you're more than welcome to hang around, but I'm going to end my recording.